as a segue from Dr. Wang and Dr. Prechaud into from the math classroom setting, I take you in a plane about 33,000 feet above the uh, the Earth and let you look down on academia as a kind of bird's eye view. And so here I do a mathematical curricular complexity analysis, and I'll explain to you what that actually is. But we're looking at data science and data engineering bachelor's degree program. And so to take you back about 3 or 4 months, I had a student in an engineering student in an advising setting that came to me and said that they were interested in pursuing a bachelor's in data engineering. And in my mind, rather than look embarrassed, I said that what's data engineering? I didn't say that out loud, but I didn't know what it was. And so I began to look at this particular entity and to try to understand. I did an analysis that was like the analyses that myself and my daughter Susannah had done previously. So I'll share all of that data with you. And so this is organized as trying to introduce you to data science and introduce you to where its place in the world, in the computational world it is, talk to you about some of the methods that we're using, and then which are ironically mathematical to analyze math. So we're using math to analyze math learning, which is interesting. And then talk about some of the results that we're getting, which were somewhat surprising. I thought that it would be a very narrow set, and it was actually very wide. And then talk to you about some of the conclusions that came out of this particular study. So, to give you an idea about what I didn't know 4 months ago and what I do know now, the rapidly emerging professional fields of data science and data engineering are due to the rapid explosion in published data worldwide. And so, like their names say, it's a call for professional data scientists towards writing algorithms to extract scientific trends. And they use a lot of different, as I say here, vogue and descriptive terminology. And so when you start reading it, it's sort of like reading a medical uh, journal article. It has lots of nomenclature that you have to look up each time you come to something that's very specific. And that makes it somewhat abstract for the general public. However, they really use, interestingly, in addition to Python and other things that the two previous authors were talking about, they use state-of-the-art tools like R and SQL and a lot of different applications that are very, very, or relatively new, but very, very, very powerful. And obviously, as our first speaker said, require a lot of electricity in terms of computational databases. But as I say here on the bottom, I think I have to move my cursor here. Um, the US data engineering and data science professionals at present are primarily graduate degree recipients. So they're really not undergrads at per se if you would meet the average person in this field. They're not undergrad graduates. They did this in graduate school, and they have a very, very high amount of responsibility and command relatively very high annual salary. So it is not only a growing, but also a lucrative field. So it is interrelated. These fields are interrelated with artificial intelligence, and I kind of try in this slide to iterate how they coalesce. So data science primarily focuses on extraction of insights from data using machine learning. Data engineering is very, very related. It is directly related. It primarily focuses on transforming the raw data into accessible and structured formats for data scientists. So data engineers are sort of working with data scientists and for them. And again, all of this is encompassed in this whole area of artificial intelligence, which develops, again, machines capable of identifying data trends ultimately. And again, we're talking about very, very, very large data sets. So while data science focuses on extracting insights, artificial intelligence focuses on building intelligent systems. So again, they are related, but one hands off to the other, if you will. So again, they are inherently interconnected. That's what I wanted you to understand. And so this growing field is involved with the entire tree of what the government likes to call operations research. So this is actually from the Pentagon, and this is actually the understanding of the central feature of operations research. And we're talking about this one arm called data science to the top left. And that's what we're focusing on. But of course, all of these are involved in the totality of the computational world at present. So again, a very exciting world, however, fairly new and fairly immature relative to math and chemistry. So professional development type of undergraduate education, I switch modes here to talking about the idea of data science as an undergraduate curriculum relative to the classic liberal arts majors that we had. So U.S. students have classically elected undergraduate majors like chemistry, physics, biology, humanities, social science, and the arts. However, if you have noticed at your university, they now elect to pursue many times the applied majors such as health and business management, engineering, computational science, or a relatively wide variety of specified programs that are meant to go directly into the professional world. So U.S. students, again, are counseled in high school, they are inundated with a plethora of prospects, and they're sometimes confused by what to look at in terms of their abilities. However, what's the major focus has been this idea of return on investment, or making it a purely economical decision in terms of career pathway, which you and I know the blessings and curses of that, but that has been the growing trend. So professional development undergraduate majors have become increasingly popular, and they tend to be very intense and densely packed with information because what you're trying to do is teach the person how to go directly into the professional workplace. And so the laboratory and the cooperative aspects and the research and the project based laboratories, again, are all focused on getting that person real professional skills that they can go directly into the industrial professional workplace. So, to give you a specific about data science and data science and engineering are inherently interdisciplinary. They are braided together or have been braided together by faculty and courses from conventional math, statistics, computer science, and engineering departments. So, the programs in the US are listed by each university, but they are supposed to be under one classification of instructional programs. And you can see on the bottom right the number of different ways that this has been captured by universities in reporting to the government. We see at least one, two, three, four, five, six different aspects that they have couched this particular major under. And so I have there in brackets the number of graduates in 2022 for each of those classifications. And you can see they add up to about 2,000. So again, a relatively or at present, there appears to be no single curricular standard like there is for chemistry when you look at the American Chemical Society, that they give an outline of what the major should encompass. But there's nothing for data science. It's so new that is out there at the present in the US. So a relatively large variance is observed in the breadth required for the knowledge base, the learning intensity, and advanced undergraduate mathematical subjects. So what I was trying to say is that each university has a different flavor and sometimes multiple flavors within the university. So many different academic tracks have been created. They've tried to combine them with geology and statistics and computational biology and so forth, and making flavors that would be attractive to students. So some universities are trying to offer dual majors where they have computational aspects that are brought in, and they feel that this is good for the future of the student's career. What we concentrate on herein is the mathematical track for BS data scientists. And so the mathematical BS data science track is essentially an applied mathematics degree with a very significant computational component. So we conducted curricular analytics, and I'll explain to you in just one second about curricular analytics. These calculations on the most mathematically oriented BS data degree that was offered by the particular university. So what are our methods? Well, our methods are couched under the term curricular analytics. If you've never heard this word before, this is a graph theory framework. So it's a mathematical graph theory method for quantifying curricular tortuosity, or the twists and turns that the curricula take. So they have several different metrics. The first is the blocking factor, which measures the extent for which one course blocks the ability to take other courses. In other words, if the student is not able to pass through one, then they are blocked from other courses in the curricula. There's also called a delay factor, the length of the longest path within the corresponding curriculum, which contains the course of interest. And so we're talking about the actual chain that it forms, and you'll see that in just one second on our graphs. And then the final one is the course complexity, which this is the sum of what I called the blocking factor and the delay factor itself. And so what we did is we added up all of the mathematical courses in their complexity and called that the mathematical curricular complexity to get a metric that understood the extent of mathematical entanglements that are in or within any particular curricula. The last one is the course centrality. This is the sum of all unique curricular pathways incorporating the particular course of interest. So all of the things that are connected to that particular course as you move forward in the curriculum. So the mathematical curricular complexity we analyzed previously for in the previous ISTIS conference, we presented on 42 different majors across the university landscape that we had data on. And so here is the mathematical curricular complexity on the x-axis and the number of bachelor's degrees that were in that particular field in 2019 and 2020. And you can see that the output here on the top right is the actual nonlinear least squares regression of this particular curve, which gave almost an exact reciprocal or inverse function. So I will be using this particular function as we move along, applied to data science from this entirety of the university landscape. So using curricular analytics on a discrete set of U.S. bachelor's degrees program, again, the breadth and depth of integration of formal mathematics, including linear algebra, was evaluated. So we were looking at how mathematics is now into the degree program. So data science curricula from 31 universities across the U.S., 25 public and 6 private, including or in addition to the Texas A&M University BS Data Engineering program. And again, data engineering, that title was only used at Texas A&M. So I emphasize that here because it is my home institution. So the mathematical curricular complexity, again, were compared to the mature bachelor's degrees that you saw on the previous slide. Right. So here is our bachelor's in data science across the country. And you can see we drew from both public and private, and we drew across the country, not really in one particular regional location. So to give you an idea of the results that we got, here is the curricular complexity graph for Stanford University data science degree. And you can see that the complexity of Calculus 1 is shown on the top right. And there, of course, is a complexity for each of the math classes, which have now been added up to get the total. So if you look at this graph for Stanford University relative to the BS degree in engineering, that you can see it's a little bit different. The shape is a little bit different. And again, the complexity overall is a little bit different. And likewise, here, this one is for Florida International University from across the country from Stanford, and is again quite different. So, differential equations lie at the heart of most engineering processes. And so, it is a central feature of almost all of the classical engineering disciplines. In contrast, here, linear algebra plays at the heart of data science. So, linear algebra is the foundational mathematical discipline that is required in all of the disciplines. It provides the matrix tools to represent, manipulate, and analyze all of the large data sets and is at the heart of the applications that have been written to date for the students to understand and use. So we were able to look at not the complexity, the delay, or the blocking factor, but the centrality of in particular, the elementary linear algebra course that was required in each curriculum. So we again centered on that. Here's Stanford University, and you can see the value here. Likewise, you can see at Texas A&M, here's the value for linear algebra, a little bit different. And here, of course, is at Florida International University, a little bit different as well. So to take all of that data and tabulate it, what we have here is the tabulation of all 32 universities in decreasing order of mathematical curricular complexity. In the third column, we have the linear algebra centrality, and in the fourth column, the world ranking, as well as the US News and World Report ranking for each of the universities. The thought process was that maybe the higher ranked or more prestigious universities might give a more robust mathematical curriculum in each case. That was the hypothesis. So here again is the bottom of the data, and you can see it. So it went from around almost to 200 up here, all the way down to below 70 over here. And if you compare that, again, above 200 or close to 200 was above nuclear engineering and electrical engineering, whereas below 70 was much like finance and chemistry. So again, very, very large range of mathematical curricular complexity. So if we take our data or the mathematical curricular complexity and assign that again to what would the mature equilibrium number of graduates be expected to be? If we were at the bottom of the chart and required the least amount of mathematics, you can see that we would expect around, from our particular modeling of the other mature sciences, you would see that we were about above 6,000. Likewise, if you look at the most mathematical that are close to 200, you would expect less than 2,000 graduates at equilibrium. So since this is so immature, we don't have those numbers yet, and those are only to come. So some unique variations that we saw, Virginia Tech University has integrated their mathematics, and you can see on the right-hand side is the normal math progression within the curriculum. And here is their answer to streamlining. They have created two 6-credit courses that encompass probability statistics, infinite series, and multivariable calculus, and then in an extension, some more linear algebra, regression, differential equations, and model variations. So they have extracted all of the mathematics that they feel are required and would be useful to a data scientist out from all of the mathematics courses that are in these particular 5 courses, right? So overall mathematical curricular complexity, if you look at this, for Virginia Tech would have decreased by about 10% if you went to this side. And likewise, the linear algebra course centrality would decrease from 46 to 35, or about 24%. So by streamlining, the question is, would you miss some fundamental mathematical problems, theorems, and proofs that might be useful as you move forward in your long-term career? So for the BS data scientist curriculum with the most integrated subject entanglements, what we would expect is again, a less than 2,000 graduates, even at equilibrium. So graduates from these particular program types would be well sought out. They would be well grounded in fundamental mathematics and hence be prone to make less erroneous extrapolations from their particular computations. So no statistical correlation was found here for linear algebra course centrality, university world or national ranking, or also for public versus private universities within the US. So at this time, no single standard accreditation agency exists, and so a number of different zip codes are used. And again, the academic credentialing is not of a single agency. So at present, the BS science degree curriculum is merely a function of whatever the US university's faculty decide. So, as an intriguing example, San Jose State University, a regional public university that's smack dab in the middle of Silicon Valley, had a significant mathematical curricular complexity of 132, which was comparable to many of the top national research universities. This is driven solely by the fact that you have all of these tremendous opportunities for BS data scientist graduates in that particular community and the industrial advisory board and alumni feedback that they receive. So, despite their very bright labor force aspect, the number of US bachelor degree graduates in data science and engineering remains very modest to date. It is a very, very high bar for a student to do. They must have advanced mathematics as well as computational techniques and the liberal arts core all in 4 years. And you can see that that is why many people elect this type of learning in a graduate environment. So, although a bit narrower than the normal mathematics, computer science, and computer engineering degree, again, they do possess real world and professional ready skills. So, our future studies will look at some worldwide universities as well as the new artificial intelligence degree programs that are burgeoning. Thank you so much for your attention, and I'll take any questions that you have.
So I had a quick question, and actually first a comment. I think it's very cool how there's a graph theory kind of induced metric to measure like the applied math side of things. Very cool. So my question is, where, and you may have addressed it, I apologize if I missed it. What was the was there like an original paper, or like what was the inception of that graph theory induced metric for this complexity measure? Very like cool and to be non-scientific, but where did that arise? That type of
2018, a professor from the University of New Mexico named Gregory Heilmann, Heilmann. That particular method was something that his group came up with. And so they were using graph theory again to develop it for curricula. And what they were looking at in their particular research was they wanted to understand if you would realign the complexity of semester by semester progression, would they have a larger graduation rate? Because they found that the more complex the system becomes in terms of the curricula, the lower the graduation rate becomes.
Perfect. Thank you very much.
Yeah,